Ever stop to wonder what's really happening inside your computer when you just, click on an icon? How does this silent box of metal and plastic seem to think? It feels like total magic, right? Well, it's not. It's actually a process, a kind of secret heartbeat, and we're going to put our finger right on its pulse.
Yeah, this is the real mystery, isn't it? What is that invisible chain of events that transforms a simple click into a fully running program on your screen? It turns out the answer lies in one single, fundamental process that powers absolutely everything your computer does. You see, underneath all the complex software and all the apps you use, your computer's brain, the central processing unit, or the CPU, it has a pulse. It's this constant, rhythmic cycle that repeats itself billions of times every single second. And once you understand this digital heartbeat, you pretty much understand the core of all modern computing.
And that heartbeat, it has a name. It's called the fetch execute cycle, or to be a little more precise, the fetch decode execute cycle. This is the absolute foundation, the bedrock of everything your computer does. Okay, so before we can actually follow that cycle step by step, we first need to meet the team inside the CPU that makes it all happen. It's best to think of it as a super specialized and crazy efficient crew, where every single member has one very specific job to do. First up, we've got the manager, the control unit, or CU. Now, this guy doesn't get his hands dirty with the actual calculations. Instead, it reads every instruction and basically directs traffic, telling all the other components what to do and exactly when to do it. Next on the team is the calculator, the arithmetic logic unit, or ALU. Now, this is the real workhorse. It performs all the actual math and logic, addition, subtraction, comparing if one number is greater than another. Whenever a number needs crunching, the control unit sends the job right here. Now, to keep everything moving at lightning speed, one part of the team is always thinking one step ahead, and that's the program counter, or PC. Think of it like the team's address book. Its one and only job is to hold the memory address of the next instruction in line, making sure there's never, ever a delay. And finally, the team needs a few little holding areas. Think of them as temporary scratch pads to manage the constant flow of information. You've got the instruction register, which holds the command being worked on right now, the memory address register, which holds the location of the data that's needed, and the memory data register, which is basically a waiting room for data as it moves in or out of the CPU. All right, so now that we've met the team, let's actually follow one tiny command on its incredible journey. We're going to trace it all the way from memory, through the CPU, and to its final completion. Probably the easiest way to picture all this is to think of the CPU as a chef and a program as a recipe. The chef reads one line of the recipe, understands it, and then does that one thing, like grab an ingredient. That's exactly how the CPU works, just, billions of times faster. And this whole process, this recipe following, it boils down to three fundamental stages. First, fetch, get the instruction. Second, decode, understand what it means. And third, execute, actually do the thing. Okay, let's break it down. Stage 1, fetch. The goal here is simple. Get one instruction from the main memory and bring it into the CPU. It all kicks off with the program counter, remember, our address book, which has the right address. That address gets copied to the memory address register. The CPU then goes and grabs the instruction from that spot in memory and puts it in the memory data register, that little waiting room. Finally, it's moved into the instruction register, ready to go. And boom, just like that, the program counter immediately updates to point to the next instruction, keeping the line moving. So now that instruction, which is just a string of ones and zeros, is sitting in the instruction register, this is where the control unit, our manager, steps in. It analyzes that pattern of ones and zeros and decodes it. It figures out, this is an add command, or okay, this is a load command. This is the aha moment where the chef reads add 1 cup of flour and knows exactly what that means. And that brings us to the final step, execute. The control unit now sends out the signals to all the right components. If it's a math problem, it zaps the ALU into action. If it's a command to move data, it manages the transfer. The action, the thing itself, finally happens. The chef actually goes and gets the flour. And the second that's done, the entire cycle starts all over again with the next instruction that the program counter is already pointing to. So that's the cycle. Fetch, decode, execute. But how on earth does this happen billions of times a second? That's the mind-blowing part, right? Well, the secret isn't just about making things faster.
It's about incredibly smart design, from where you put your memory to building a literal assembly line for instructions. A huge piece of the puzzle is just real estate. Location, location, location. Those registers we met earlier, they are physically inside the CPU, built from ridiculously fast memory. But your main computer memory, your RAM, is outside the CPU, and it's much, much slower. The difference is massive. Fetching from RAM is like a long walk to the pantry for an ingredient. Using a register is like having it right there on your cutting board. That's why those little internal scratch pads are so incredibly important. And these physical design choices create hard limits. Take, for example, an old CPU with a 16-bit memory address register. That means it can only create 2 to the power of 16 unique addresses, which is exactly 65,536. This physically limits that processor to talking to, at most, 64 kilobytes of memory. That's it. The physical size of these internal parts directly dictates the power of the whole computer.
But maybe the cleverest trick up the CPU's sleeve is something called pipelining. See, instead of waiting for one entire instruction to finish its whole fetch, decode, execute journey before starting the next one, the CPU works like an assembly line. It starts fetching the next instruction as soon as the first stage of the previous one is done. Just look at this table. It lays it all out perfectly. In the very first clock cycle, instruction 1 gets fetched. In the next cycle, while instruction 1 is being decoded, the CPU's already fetching instruction 2. By clock cycle 3, look at this. 3 different instructions are all in the works at the same time, just at different stages. This overlap means that once the pipe is full, the CPU is completing an entire instruction with every single tick of its clock. It's a massive, massive efficiency boost. So let's pull back for a second. We've met the team, we've followed a command on its journey, and we've seen how it all happens so fast. What does this all really mean? What's the big picture here? And here's the thing that's just so cool about all of this. Everything you do on a computer, I mean everything, from browsing the web to playing a complex game to just writing a document, it's all built on this one simple, elegant loop. All of that unbelievable complexity just emerges from the ridiculously fast repetition of this one simple process. So to wrap it all up, at its very core, computing is just a logical, predictable, step-by-step process. The CPU isn't one single brain. It's a team of specialists, with the control unit as the manager and the ALU as the calculator. That fetch, decode, execute cycle, that's the basic heartbeat of it all. And all that incredible speed comes from really smart design, like using fast internal registers and the assembly line magic of pipelining. You know, this simple idea, this basic loop, has been the engine behind our entire digital world for more than 50 years. But as we start to push against the very limits of physics, it really makes you wonder, what comes next? What will the fundamental heartbeat of computing look like in another 50 years?